Okay, following, we would like to introduce the mountain groundwater flow. The groundwater in the plain is often used for public waters. Understanding and evaluating groundwater recharge is crucial for the groundwater sustainability. So even commonly we doing the groundwater pumpings in the plain area, but some of the waters is come from the mountains and some of the water is from the surface recharge. And right now, we found that the mountains recharge could be one of the important issues. Okay, so in the previous research, they also found that the mountain to the lowland freshwater supply vary from 20 to 50% in the humid regions, and to 50 to 90% in the arid regions. So the mountain block recharge, the MBR, is particularly significant due to the natural barrier created by slope and also the valleys that can block or redirect the water flow. So we have several terms here, we call the mountain front recharge, mountain block recharge. Mountain front recharge is the waters, they come from the slope angles like this. So commonly when we have the mountain or we have the foothills, they commonly have the geological structures besides. Like we have maybe we have the fault, like the flat fault or normal fault around to induce the mountains to form the mountains. And the mountains, they have the waters like a runoff or surface runoff here, and some that will go into the groundwater system. So we call this the mountain front recharge. And here we have the ABC areas. So the researchers, Wilson and Grant, in 2004, they try to separate like the A could be like vegetations, predominant angles or the plant angles. They have the different recharge the abilities or have the different recharge behaviors. So here's the information for you for your reference. So if you would like to have the recharge or if you would like to set up like the artificial recharge, you can also consider this kind of properties because they might have the different recharge abilities. And in the mountain block recharge or the mountain front recharge systems, commonly we can separate to several categories. And in the system here, we have several terms like the focused near surface recharge or the diffuse near surface recharge. Focus means they have the huge amount of the water recharge, like they might have the rivers, and they when they outflow to the mountains, they have the sediment or the riverbed, so the waters is accumulate quite much, and they could be able to recharge to the plain area, so from the mountain to the plain. So we call this the focus. And we still have some of the diffused surface recharge, like they might have the surface runoff, and after they run out of the mountains area, they will directly recharge to the groundwater system. So they are like diffused behaviors. And another is that we call the focused subsurface recharge or the diffuse subsurface recharge. Focused subsurface recharge, they could be due to like the fault systems. Commonly, we know that the fault could be separated to permeable or impermeable. If you have the ruptures behaviors in the core areas, commonly we have the fault gouge. Okay, the core zone of the fault, they are become commonly they are like the clay material or the fine-grained material, and they are impermeable. So we are not able to have the groundwater to float. But besides the fault zone or the cold zone areas, they have the damaged zone. And originally, if they are the rock system, they are not able to have a huge amount of the porosity or the fractures for groundwater to flow. But in the damaged areas, they will create a lot of pore spaces, and water can accumulate or flow through that area. So the fault systems, they can play two roles. One of that's permeable channels, they induce the preferential flow paths, so the groundwater will concentrate to that area. And another could be like a barrier system, they prevent the water to flow through it. Okay, and in these kind of systems, if you have the fault zone or damage zones, they become the focused subsurface recharge. They will be very concentrated, like the fault system. They can accumulate or become the channels. And the others, due to like the small fracture or the tiny fractures, they still have some of the waters can flow from the mountains and balance the surface and go to the plain area. So they have to diffuse the subsurface recharge behavior. Okay, we can separate to this four kind of category. And this is the very commonly conceptual diagram showing the four major flow paths in the mountain block system. Commonly, if we have this is a profile, so from the mountains and to the plain area. So the system here is for the rock system, and here could be like the alluvial plain areas. And as I mentioned, commonly if you have the mountains or the foothill, you might have the fault or geological structures occurred around. And commonly we will imagine like the river system or the valleys. So the groundwater will flow to these areas and outflow, like because they're 3D, so they will outflow to another directions. Okay, so we have the local groundwater flow system. So from the mountains flow to the rivers like that, and we have the intermediate flow system, like they might penetrate this river system and to the lower part, we call it intermediate. And much deeper part could be they flow this direction, called the regional flow. Okay, so they can move in very deeper and outflow to the plain area. And another is we call the front slope, like they are the final one, final mountains. So the waters directly flow to the plain area. Okay, so we call this is a front slope float. Commonly, if we have the mountain or foothill, we'll imagine that they will become like the water divide. So that what divides means the waters. If you put the waters here, the water will flow from the divide on the right hand side. They'll flow to the right. From the left hand side, they'll flow to the left. So this one become the water divide. So this is what we expect or imagine the groundwater flow system. So they will look like this. But in the following, I will show the different patterns after we using numerical simulations. The result is different or different from our expectations. This is another researchers, they try to use in the subsurface saturated unsaturated flow field with the mountain block bounded by a basin and a range type and high angle normal fault with the basin field sediments. So they using the system like they have the fault here and they doing the simulations to let the water flow, like they have the arrows means the water flow rate. So the water can flow through the fault system and go to the plain area. So that's what they observed. But honestly speaking, this figures is not correct. For example, they have the head values. They're using the head here. We can see that the head is high here and lower decrease with the with the depth. Okay, that's what they illustrate. But I want to say that when we using the head concept, that means the head is from the water flow will be flow from the high head to the low head. They were not able to flow through the different or close to the head system. Okay, so you remember that the head is the driving force for the water to flow. And for example, if we take a look here, that means here is the high head, lower, and much lower like that. So that means the groundwater flow should be from the bottoms to the shallows, from the bottom to the shallows. But you can take a look their flow directions like this directions, not this direction. Okay, so that means this one, this figure is not correct. For their flow rate, I think it's correct. But for the head values should be wrong. They illustrate that the deeper will have the high head, the shallow will have the low head. These illustrations means they are using the pressure head, not using the total head. Because we mentioned that the head, the total head or hydraulic head include the elevation head and pressure head. Pressure head means when you have the deeper, you have the high pressures. So the deeper the high pressures will occur, like these patterns. So this is the pressure head. Okay, not the total head. Total head should be, this one should be higher. Right hand side should be higher head, and the left hand side should be a lower head. Okay, so this is total run for the head values. Okay, so this is to illustrate that if you have the fold or you do not have the fold, like if you have fold and this is the barriers, so the groundwater cannot fold penetrate. But if your fold disappears, the groundwater flow will be more smoothly, and they can able to penetrate the whole system like this pattern. Okay, so your geological structure will also affect largely for your groundwater flow patterns. For the mountain block recharge or the mountain recharge systems, this is the map in the world they doing the research before 2004 or after the 2004. So before 2004, you can see that the number of the investigation is not much. It's not many. But after 2004, the research become increased largely. They approach to 20 or 30s for different type. So this is the map. We can separate to the basin focus. So they mainly based on the basin. Basin means they study like the plain areas. Because there's mainly for the groundwater resources. And the mountain block focus, that means they focusing on the mountain block and combine the basin to the mountain block, like the study we would like to show later. So this is the basic mountain block, or the okay, this is the accumulations quantity. So we can take a look that the US have a lot of mountain issues, okay, mountain block issues. And like in Taiwan, we have several. In Japan, China have some. India or in the Africa have several. And Europe will also have another hotspot, okay. So that's very common. So we expect that Europe and the US will have more research about this. Then here's the reference list. To let you understand how they using the what kind of methods to doing some investigation. And this is the locations, this is the publication or the authors, and what's the type, like basin or the basin to the mountains, and the climate conditions, and also some other lethargies informations. So in Taiwan, it's Professor Peng Zhongren. He mainly using the isotope to do the studies. So they have several studies in Taiwan to show the hotspot in the previous papers. And following, we introduced the study background for our research. Okay, the Geological Survey and Mining Management agencies they proposed a plan to investigate the groundwater and hydrogeological around the boundaries between the mountain to the plain areas. Like these figures, in the past, the GSMMA or CGS, Central Geological Survey, they try to investigate the groundwater system in the mountains. And right now, these phases, they try to focusing on the boundary area from the mountains to the plain. So they separate the years, different years, they will focusing on the different areas to understand like the foothill behaviors or the groundwater flow in the foothill area. So right now, this first phase is from 2022 to 2026, with each year focusing on one areas. And this studies is focusing on the Dodo foothill. Dodo foothill is this area in the southern Joshua River Vietnam. And the study area is across the Dodo foothill to the southern region of the Joshua River Vietnam. So in our studies, we will use in the cross sections from the foothill, little mountains and foothill, and then go to the plain area to see how the water flow behaviors look like. Okay, so the study area, we try to draw the area like this. So this is Joshua River, and these areas, the polygons shows the Joshua River VFN. So we try to have the cross sections here. And the background is that in the previous study, they have the geological informations. They try to understand what's the geology. They have the Togosan formations, the Gluvian and alluviums, and also the mountains, and also like have some rivers penetrate. Okay, and from the hydrogeological informations, you can see that in the proximal fan area, commonly you will have more gravels, and then going to the coarse sands, fine sand, and clay interbedded. So this is the geological structure proposed by GSMMA. And in these areas, because we collaborate with the E-trees, they try to doing some investigation like a geological survey or geophysical surveys, try to understand what's the structure of this. So this is the profile AA and BB. So you can see that AA and BB here. And in this area, we have some anticline, and we have some Tokusan formations, and also have the Dongshuhu fault. But honestly speaking, we don't exactly know the location of the Dongshuhu fault. Even we're using the geophysical surveys, but it just approximately define the area. Okay. And BB prime, we can also have another much complex structures, so they can using the geophysical methods to identify the locations and the orientations for the fault. And our study will mainly focusing on the AA prime to understand the behavior, water flow behavior. And we try to collect the hydrological observations because we want to have the simulations more approach to the realities to understand the real water flow system and also some of the hydraulic inferences. So our cross-section is around this area. So we try to collect the groundwater observations around. So here's the groundwater observation curve. Okay, we have different depths. The wells have different depths. We have the serial groundwater observation with 3 different depths. We have the rainfall patterns. So we can use in the rainfall to set up the recharge and using the groundwater observations to set up the boundary condition. And try to have the geological models. We try to combine the central geological survey result and geophysical survey result. So as we mentioned previously, this is the geological structures that we will follow, but they do not have much detailed informations. And in the previous, they have the Tokusan formations and also some other like gradual formations here. And this is the alluvial fan area. And they might have some layer system like this kind of patterns. So if we're using another conceptual model like this, geological survey provided, we have some of the sediments, alluvians, and we have some the alluvian here is this is the alluvians, and we have the geological structure for the sediment area, and this is the rock area. Okay, and we might have some formations and any crime systems around. So we try to combine all of them together to draw our conceptual models. So this is our conceptual model we have. So as we mentioned, we cut from around this area. We're using the Dajianshan fault to be the boundary, boundary on the right hand side. And we have a small river and Jinshui River, and this is Doliu Foothill. And after that, we have the Dongshuhu fault here, and we have the alluvial fan area. We have the different material, or they become a layer system from the gravel, coal sand, and clay. And we have some Tokusan formation and Jinshui shale formations around to form this structure. And the numerical model that we developed is using the polyidentity theories and using the COMSOL multiphysics with the finite element methods. Okay, so we try to using our conceptual models. We draw a conceptual model first, and then we try to input it to the COMSOL multiphysics to construct our numerical model systems. And the Groundwater equations that we adapt is, as I mentioned, we're using the polyidentity theories. We combine the water flow and also the displacement field together, because the main purpose is that we would like to understand not only the water flow. We hope we can try to extend the studies to understand how the mountain flowed to the plain area to affect the land subsidence or even some of the uplift behaviors. So that's the reason we're using the hydromechanical system, not only the groundwater flow system. Okay, and the detail I don't want to emphasize too much. But we'll consider like the gravity for the fluid and solid to see how the gravity influences and reach the steady state condition. And here's the parameter that we set up in the system. Also, I skipped this because we just let you understand some physics. And for the boundary conditions, because if you're doing the numerical models in the futures, remember that all the boundary you need to describe in very carefully and clearly. So for the hydraulic boundary conditions, we need to set up all areas to have the suitable boundary conditions. Like the upper part we set up could be like the recharge boundary, or in the beginning we're using the no flow to see only the water flow pattern. And on the right hand side and left hand side, we're using the specified head because we have some observations point and using some assumptions because the right hand side we do not have observations. So we try to use an assumption to do the settings. And the bottom is the no flow. We assume there's a no flow, so the water cannot penetrate. Okay, so there's some of the assumption. And the same, the mechanical boundary, we also need to do the settings. So the free boundaries on the ground surface, that means the water, the deformations can occur on the surface without any constraint. And the bottom and the right and left hand side, we're using the lower boundaries. That means we only allowed the transverse deformation, but not allow the vertical, the normal deformations in that area. Okay, that's the. I do not explain too much in the detail. And let's take a look at the result and discussions. The first topic we want to understand the water flow from the mountain, from the rock to the sediment system. We're using two scenarios. This is very simplified. We only using the rock, and this is the sediments. Okay, so the consolidated sediment and also the Tucson formations. And we consider this is the no fault system. This is the fault system to see how the influences. Okay. And the first is we do not consider any fault. So we only have the water flow from the right hand side to the left hand side. And very interesting is that because this model we're using the no flow on the top surface, so they do not have any influences from the vertical directions. So the water flow, you can see they will like climb into the mountain, but this is not the correct. Okay, that is just show the pattern. An interesting part is that we can see the water flow from the rock system to the consolidated the sediment systems. They will have uplift behaviors. Because we set up the different K value, hydraulic conductivity we mentioned in the previous talk, we're using the high K values for the sediment and low K value for the rock system. Because commonly the rock is the consolidated or they are cemented, so the hydraulic conductivity will be small. They are not easy to flow. And the sediment, because this area, called the proximal fan area, commonly is the gravel or the colluvium, so they are like larger grain size. They are easy to have the flow. So that means this one become very high K, and they can generate waters very fast, and they will induce like we call a sink concept. So the groundwater will be abstract by this sink. So we can see that the ground flow become uplift to the system, to the proximal fan area, and then go into the distal fan area or the middle fan area. So in the previous, we might imagine that the water just flow grows smoothly to the plane. They do not have different disturbances. Okay, and we try to understand how the hydraulic conductivity affect the behaviors. So we try to change the K values, like increase. If we increase the sediment K values, like original is 10 to minus 3, and we decrease the K values, so it becomes more, and much smaller. Okay, so when we decrease the K value for the sediments, so you can see that the water flow patterns become relatively smoothly because they become more homogeneous. The K values between the sediment and the rock will be similar, so it becomes smoothly. So the water can flow smoothly, as we mentioned. If the if the system is homogeneous, we'll expect that the water flow from the right to the left-hand side is very smoothly. So that means it emphasizes that if we have the sediment area in the rock system for the larger K differences, it will induce like the sink system to abstract the water to float. Okay, and this is the displacement field. Seems we do not discussing too much about this, so I skip this more quickly, just to let you see that if we increase the K values, so the sediment, the water will outflow and induce like the uplift of the behavior in the proximal fan area. Okay, and this is some quantification. I skip this part. For the second scenario, we using the fault system. And the fault system, as I mentioned, they could be permeable or impermeable. And if we using the fault of the K to be a permeable system, so they become the channels. So you can see that the water flow will be absorbed the same. Like this one is the sink, and this one, the fault become also a sink. So the water will flow uplift or for the downward to the this kind of sink system and going to the plant area. And if we set up like the low K values, they become like a barrier. So the water cannot penetrate, so they become only the uplift behaviors. They enforce the waters to uplift to the proximal fan area. Okay, so there's another system to let you see that the differences. So if you have your fault is channels like conduit, so they will induce the water to become the recharge to this area. But if no, they will mainly recharge to the top area, the proximal fan area. Okay, so this is many differences. And displacement I escape. Okay, and comparison escape. And the second part is we try to using like hydrological inferences, try to understand how the hydrologies affect the result. So in this scenario, we put the Qingxue River. In the previous scenario, we using the no flow on the top surface, but right now we try to using like a recharge. We set up the recharge. We set up the Qingxue rivers to see how they look like. And the Qingxue River, one of them we set up arbitrary for the river levels, and the other we using the observation for the Liu Bridge. Okay, to see the differences. And if we have the river and recharge, we can see the flow pattern is quite different. Okay, so like if we have the rivers, they will have the like a kind of sink. So the water from the mountains will upward to like the discharge to the rivers, and the river part will also have the recharge to the water system and then flow to the downstream area. Okay, so this is the main differences. But the interesting part is that, as I mentioned, commonly we see from the previous conceptual model. I try to enlarge this. In the previous, we mentioned that commonly we imagine the foothill or the mountains will become the water divide. So if you put the water particles on the left-hand side, they flow to the left, and put it on the right-hand side, they flow to the right. But from these systems, we can see that the groundwater particles on the right-hand side, they flow through the water divide. We imagine the water divide and directly to the downstream area. Okay, so they can penetrate directly to the downstream area, and so the local ground flow is not what we expect. And this one could be the intermediate ground flow. We can still see that they will penetrate and then flow to the downstream. But we do not see the regional flow because I'm thinking maybe the depth is not sufficient. So most of the water will outflow to the river. They do not show the much deeper flow to the downstream area. But like this kind of the pattern we see again, if we can have the water flow patterns, the groundwater particle on the right hand side will directly flow through the water divide to the downstream area. So this surface water divide, they occurred for the surface, but they might not play the important role for the groundwater system. So totally different from our expectation. We need to be careful for this behavior. Okay, and we try to do some further investigations, try to using like the Tinshui River, and try to set up the different quantity to see how the ground flow patterns look like. Okay, seems the result could be similar. I will skip this part, but found there'll be a little differences that we can see that some of the ground flow pattern they still flow balance the surface and discharge to the alluvial fan areas. So even though they will form like a sink I mentioned in the previous cases, but if we can have much deeper, or we can have much circulation, so we might have much deeper circulation flow path. And the Tinshui River will become like the discharge area, so the water will outflow. Okay, so displacement escape and compression escape. And following is we try to understand the geological inferences because we hope to simulate the behaviors into a more approach to the realities. So we try to understand how the geological system affect the result. And here we, well, this is the same settings, but we try to consider like if we have the fault, if we have the formations, and we also have the side, like the alluvial fan area, we'll have the different geological materials to see how the influences might have. Okay, so if we consider like a quite complex geological structures or geological formations, the water flow right now, this one we do not consider the river, so we only have the water flow from the right hand side to the left hand side, and we can see that the groundwaters can penetrate some of the we call the Tinshui shale formations. Even they are very low K values, but I think still some of the water can penetrate, and some of the groundwater will uplift to the mountain because, as I mentioned, we have the no flow, so they will enforce the water to uplift. And we can see the patterns that groundwater can penetrate some of even the strata or the formations. And if we have the fault system, and this fault could be permeable or impermeables, and right now we're using the permeable, so the water can following the fault to discharge to the downstream area. And even the water flow in the sediment area, you can see they have sometimes they have the uplift or the decline behaviors because they are quite arbitrary. You can take a look. They have some clay material or the coarse sand material, so the water flow system will have a more complex behavior. And this one is to combine with the deformations, because I mentioned that we would like to understand how deformation might occur for the discharge from the mountains. So the materials like the clay, they are more easier to be compressed. So we are easy to see that the clay material, they have the larger contribution for the subsidence. So this area can have the more significant subsidence quantity occurred. Okay, so just let you understand if we have the more complex situations, what they look like. And in this scenario, we try to combine the river and the recharge on the ground surface to see how it influences. And in these cases, the result will be more approach to the reality because we have the rivers, we have the rainfall recharge, we have the formation, we also have the fault system, okay? Okay, and maybe we try to enlarge this area. Okay, so if we have the river or we have the recharge quantities, the first part we can take a look. We have the river and river here. So the groundwater system, if you have the recharge, they will become like outflow, and even very deep, they can still uplift to the river system. But some of the waters, they are not able to be catch up. Commonly we use the the capture zone concept. Okay, so this is the kind of capture zone concept. So the water here will be captured by these rivers, but some of the waters they can flow to the downstream area, and like this they flow to the downstream and discharge to this river again. And as I mentioned previously, this kind of small mountains, they are not able to form a water divide. So the waters from the right-hand side can flow through the mountains and go to the river system. And in this area, we can also see that they have the local flow. So the water flow here, they can flow back to the rivers, but seems we have the formations here to disturbances. So some waters flow back to the river, but some flow, they still able to penetrate the strata or even the shale formations to the downstream. And some of the much deeper groundwater flow will also follow in the formations and then even penetrate the formations to the fault system. And groundwater will flow through the fault system. And some of the formations, they are able to have the penetrations behaviors, so they will flow to the downstream. And some of that become like a conduit, so the ground flow will uplift and then recharge to the proximal fan area and go to the fan area to have the recharge behaviors. And the same, the ground flow in this system, they have the quite arbitrary because they depend on the geological material for the flow patterns like this. So in this area, in this system, we can see the front slope flow. As we mentioned that from the lattice one, the groundwater flow for this part we call it as the front slope flow, and the local flow, as I mentioned, this is the local flow. They flow back to the river system, and we have some regional flow. They go to the deepers and then go into the friend area like that. So we have several different kind of the flow patterns we can show up in this figure and result. And the same, we try to understand how the system, how this system affect the compactions or the subsidence in the friend areas. Okay, so we'll try to quantify that. And the red color means they are compressed. And if we have some blue color, that means they are uplift. But it seems the water flow is quite slow, so we do not be able to see the uplift. But if we we set up some scenario, we can have the recharge from the rainfall. For example, if we have the typhoon events, we can have the scenario to have the recharge largely in the mountains area, and we might be able to see compared to the original system, they might have the uplift behaviors due to the rainfall recharge system. Okay, and here's some comparison. I skipped this part. So very quick to conclude these mountain flow behaviors. The behavior of the groundwater flow from the mountain to plain area is different from the conventional concept. As we mentioned, that commonly we treat the mountains to be the water divide, not only the surface water, also the groundwater divide. But in our simulations, we can see that this water divide is not very precisely occurred when we doing this kind of simulations. And even we can see some of the behaviors different, like the alluvial fan area in the top fan, in the proximal fan, they become like a sink. So they will induce a suction for the water to uplift in this area. And these behaviors also support commonly we see for the reality, because commonly in the proximal fan, distal fan, and middle fan area, between the proximal fan to the middle fan area, commonly we will see the spring or the flowing artesian well in the physical behaviors. And we don't know exactly how they form this, and from this research we can demonstrate this kind of mechanisms, because they have the uplift behavior. So this kind of uplift flow will induce the flowing artesian well, and also they will be able to support the spring. And even for the subsidence area, we commonly also see that in the middle fan area, they have the significant subsidence, but even we cease the pumpings for deeper pumpings, but they still have continuous subsidence. And I'm guessing that this kind of the subsidence is due to originally we have the continuous uplifted flow patterns, but right now the flow is be cut or the flow become decreased. So they do not have the strong recharge behaviors and induce the decrease of the uplift flow and induce the subsidence occurred, because subsidence is the compared result, and the water flow system is like also the comparisons. If we have continuous supportings, the surface be supported. But if you decrease the supportings, the surface will have a little sink. So this is the possibility to describe in this behavior. And when the high K or the low H values is nearby, the high K like we call the sedimentary material, and low K like the rivers, they will form an important sink for the water to discharge. Okay, like in the proximal fan area or in the river system, they become like a very strong uplifted behaviors occur. And fold play an important role for water to flow from mountain to plain area, which might induce the spring or the flow artisan well systems, as I mentioned. And water flow from mountain to plain areas result in supporting the land surface. With a decrease in water flow, then subsidence can occur. Okay, that's what I mentioned. We see that. Okay, so this sharing is to that you very quickly understand what we are doing for the recent years. We collaborate with the E3. And in the previous, we do not have this kind of simulation. We're just using the general concept to understand the water flow in the mountains. But recently, we're using like this 2D modeling system to understand some of the water flow patterns out of our expectations. And in the future, we will try to develop the 3D system, because as we mentioned that we have the river, but we right now just have the river to cut here. But the 3D system, we have the river to outflow. So if we have the 3D systems, what the result might look like, or what the result could be more approach to the reality. And the other, we can try to use a much deeper thickness for the models to understand if we can see more clearly the regional flow patterns, like they can flow to the ocean area, maybe. That's another part we will try to emphasize in future. Okay, I think we take a break here, and later we will show you another is the summer rainwater discharge issues for to understand the other water cycle system. Okay, thank you very much.